Hi guys, today's video is going to be about using this parent function that we've talked about the other day and we graphed it the other day. Today we're going to be talking about problem solving and how to do that. So let's take a look. Remember that with that function, this parent function, we know that the first number is the starting amount, the second number is the growth factor, and then that x is time in whatever capacity the time is measured. So if we look at these examples, we're going to talk about what is the starting value, is it increasing or decreasing, that is it exponential growth or exponential decay, and then what is the percent of the growth or decay. I'm going to do a couple of these with you, and then I'm going to ask you to do a couple of them on your own. Let's look at number one. On the first one, the initial value, the starting value is 1. It starts at 1. Is it increasing or decreasing? Do you remember that if that number is above 1, it's increasing. But if it's in between 0 and 1, it is decreasing. So this one is decreasing. And the second part, or the third part, is what is the percent of growth or decay? Well, if we think about this, we have a 0.5. Doesn't that mean half? So doesn't that mean we are losing 50%? So we have a 50% decay on that problem. We're going to talk a little bit more about that part C as we go along. We're actually going to go over here to letter D, okay? So our starting amount, our increasing or decreasing, and then our decay. See what you can do with that and we'll talk about it. Okay, for this problem, it's going to start at 12, right? It's starting at 12. It's going up. How do I know it's going up? Because it's above 1. Okay, it's going up. How much is it going up? Well, the 1, if that was just a 1, it would just stay 12 the whole time, right? So the 1 is just like maintaining that 12. The 0.7 is 70% because you guys know that 0.7, we would move it over 2 decimal places and get a 70%. So that is growing by 70%. Okay, the next problem, we can see that it starts at 5 and it is decay because it's less than 1. And so since it's less than 1, it is going down. And then how much is it going down? Well, it's only keeping 20%. If it's keeping 20%, that means the decay must be 80%. Over in the margin here, I wrote out this formula because this is another form of the original formula that we're talking about. It's just now, let's talk about, well, how much is it going up and down? So that R now is the percent of growth or decay. And really, there probably ought to be a plus and minus here because it's either going up or going down. And so as I've been looking at these, I've been kind of thinking of this. You haven't known about this formula, so you didn't know. But let's just quickly go back and look. For letter A, this problem is 1 minus 0.5. That's how we get 0.5. And so it's decay. This one is 1 plus 0.7. That's what makes it growth. Okay, we're going back and thinking about this 1 plus or minus R. This one is decay. How much? Well, it's 80% decay because I ended up with a 0.2. So that's how that works. Okay, so we are going to kind of be using both of these formulas a little bit interchangeably. This one I think is a little bit, it makes a little bit more sense. But sometimes formulas are written this way. So we have to understand both of them and understand how to work between them. Take a second. The next couple of them aren't maybe as direct. F definitely is. You could definitely do F. But take a few minutes right now to look at these other ones and see what you come up with. Okay, let's look at these other ones. We left on E. E starts at 0.45. I deliberately tried to trick you up on this one by putting the decimal here and the whole number here because we've been seeing it the other way. But this is a 0.45. That's where it starts. It could be 45 cents. Who knows? And then times 3 to the x. Now this is a whole number. It's not like a 1 point, it's the whole thing. That means it's multiplying by 3 every time. That's a 300% growth. Part C, or question C. It is written as 2 to the negative x power. Well, doesn't a negative power mean a reciprocal? And so I could actually rewrite this as y equals 1/2 to the x power. And that would mean it would start at 1. That 1 is an invisible 1 there. And it decays by 50%. Example F starts at 129 and goes up by 63%. So that's how you look at the formulas. Let's look at some examples now of how to use that. Okay, let's think about this formula as well as the one up above and how we can put this information into that formula. So read through the problem, and our starting amount is 281 million. Now it's 281 million. I don't have to write all those zeros. I can just write 281 and then do my calculation and then add on the word million at the end. So it's 281 is my starting amount. It's increasing 1.24% annually. 1.24%, if I move that decimal over two places, is 0.0124. And so in my parentheses, I'm going to say it's growing, right? So I'm going to say 1 plus 0.0124 to the t power or to the x power. It doesn't, that letter, it stands for t, but it could be a t, it could be x. That's going to be my formula. I could also write that in the shorter way. And so my shorter way would just be to call that inside part 1.0124, because 1 plus that is that, right? Okay, use your function to approximate the population in the year 2010. I'm going to show you how to do the calculator, but before we do that, let's write down an equation that we will put into our calculator. All right, here is the equation. The only thing I changed is I put in a 10. Where did I get that 10 from? Well, if you look back at the problem, it says in the year 2000 there's 281. Now we're asking about what about the year 2010? Well, that's 10 years later. And so that's why t is 10. It's not 2010, it's just 10 years after the original thing. Okay, let's go to our calculator and see how to put this in. Okay, in your calculator, just in the regular calculator section of it, not the graphing part, just the calculator section, put in 281 times 1.0124. I used parentheses because that's how it is in the problem that we wrote on our paper. Now, the power, this button, this caret button that's above the division button, that's how you get to the exponents. And I'm going to put an exponent of 10 in there, and I get this number. This is 317,854,000, blah, blah, what is that? And then 2.7. So on my paper, I'm just going to write 317.85, okay? But it's going to say million. But that's how you do it on your calculator. So my answer is 317.85 million, and that's the population. That was an increase problem. This next problem is a decreasing problem. So take a second to read through the problem and decide what could we come up with for an equation. All right, because it is decreasing, we need to talk about what do we do with that decreasing. Remember, 3.5% is 0.035. I moved the decimal over two places. If I took 100% minus 3.5%, I would get 96.5%. Or in other words, if I use that formula that I wrote down on the margin up here, and I did 1 minus, because it's decay, r, I would be taking 1 minus 0.035. And so then my equation comes out to be 80, that's my starting amount, times 0.965 to the t power. So I go to my calculator and I'm going to plug this in. I'm plugging it in to the 5th power because it's 5 years later, so I want to put that in my power. And then when I do that on my calculator, I come up with between 66 and 67. I don't remember the actual decimal, but when you're coming up with these models, you're not going to predict exactly how many animals there are. Maybe, sorry, but maybe one of them got run over. Maybe, who knows, okay? So we're predicting an approximation. It's an approximation. So it doesn't have to be exactly 66 or exactly 77 or 67. It's just an approximation. Okay, one last problem, then we will be done for the day. Take a look at this and think about how you're going to come up with an equation for that. Pause it here and come up with an equation. Okay, your equation should be something like y equals 34 times 1 plus 0.26. It's going up by 26%. Or you can write it in a simplified form and just call it 34 times 1.26 to the t power. Now we need to figure out what to put in our exponent. Well, if it went up from 1995 to 1999, how many years is that? That's 4 years. Take a second to put that in your calculator and see what you come up with. Okay, you should have come up with 85.7. That is in millions. You have to go back and look. They're talking about millions here. So that is 85.7 million users. And I wouldn't round because 0.7 is 700,000, and that would be a lot of people you're rounding. So I wouldn't round that any more than that. Just leave it there. Okay, there will be a couple different choices for you to do for homework from this lesson.